All right, so we're going to do Chapter 2, Section 1, Introduction to Limits. So basically, 2.1, 2.2, and 2.3 is a lot of setup, a lot of theory, okay? So bear with me as we go through it. I'm going to highlight what's super important and what areas are not so important maybe. But as we embark on a journey in the study of calculus, it is reasonable to consider how calculus differs from algebra. Algebra ends, calculus begins. The words static and dynamic capture the essence of the difference between the two mathematics disciplines. In algebra, we solve equations for a particular value of a variable, a static notion where we just find the answer. But in calculus, we're interested in how change in one variable affects another variable, a dynamic notion. So in algebra, we solve. In the calculus, you're going to hear rate of change, instantaneous rate of change. How are things changing? That's the big difference between algebra and calculus. Okay? Concepts of calculus were developed independently by Isaac Newton of England and Gottfried Wilhelm von Leibniz of Germany. They sought methods of solving problems concerning motion. Calculus today is used in physical sciences, business, economics, life science, social sciences, any discipline that seeks to understand dynamic phenomena, how things change, how temperature change, revenue, cost, profit, how everything, motion, how things change, that's calculus. And in this chapter, we introduce the derivative, one of two key concepts in calculus. In a later chapter, we'll talk about integral, the second key concept in calculus. Each of the concepts depend on the notion of a limit, which is explained in 2.1 and 2.2. The graph of a function is a graph of the set of all ordered pairs that satisfy the function. So if I had the function 2x minus 1, and I said x is 2. Well, if you plug in 2, what do you get for an answer? 3. So f of 2 is 3. You got the answer 2 comma 3. If I said x is 0, what do you get for an answer? So you have the answer 0, negative 1. If I said x is negative 1, you have the answer of negative 1, negative 3. Those are things we know. You plug in a number, you get the result. That point is on the graph. And all those points together make a line. So in this again, we talk about linear. F of x equals 2x minus 1. That's what it would look like. Okay, every point is on the line. We totally understand all that. Okay, and if I use this line, I can go the other way. I can find answers. So if I use this line, when x is negative 1, what's y? 5. We can go both ways. When x is 0, what's y? 2. When x is 1, what's y? Negative 1. When x is 2, y is negative 4. Okay? All things we understand, all things we've done before. Okay? So the limit of a function at some domain value x equals a involves examining the behavior of the output values of a function as the input varies increasingly closer to the domain. So the limit means as we get closer, as we approach. So if I asked you, what happens when x is 2? You would plug 2 in and get what? 3. We know the answer is 3. But I want to know what happens as we get closer to 2. What does it look like? So if I go 1.5, I get that answer. 2. 1.9, 2.8, 1.99, 2.98, 1.99, 2.98. What is it getting closer to? 3. No, this is how it works. From the left, what number is it getting closer to? 3. If I go from 2.5, 4, 2.1, 3.2, 2.01, 3.02, 2.001, you get 3.02. From the right, what is it approaching? 3. That's a limit. That's the big thing about 2.1. As we come from the left, it approaches 3. As we come from the right, it approaches 3. It's approaching a certain number. That's what the limit is saying. Okay? And we already know the answer is 3 because I can plug it in. But we can now say, this is the technical stuff, the limit as x approaches 2 gives me an answer of 3. And if you plug in 2, you get the answer. Okay? That's the idea of a limit. That's the idea of a limit. So if we had the graph x plus 2, and I want to find out what happens at 2. Well, all of us know if I take 2 and plug it in, what's 2 plus 2? 4. You already know that, right? I know the answer is 4. We're going to do more complicated stuff. We're going to do how things change. But the answer is 4. Coming from the left, what number is it approaching? 4. Coming from the right, what number is it approaching? 4. It's further evidence that the answer is 4. Okay? But we use the word limit as it approaches. So we can say the limit as x approaches 2 gives us an answer of 4. And you're like, why am I even doing that? I know the answer is 4, because we're going to do harder stuff. We're going to talk about rate of change. We're going to talk about, as we get closer, what happens there. So we write the limit as x approaches some number c, f of x equals L, and that function will result in L, x as it approaches L, and x as it approaches c. And the existence of a limit at c is independent of the value of the function at c. In fact, c may not even be the domain of f. However, the function must be defined on both sides of c. That's really the bottom line is we're looking at it from the left and we're looking at it from the right to make sure that's the answer. Okay? So if we do the absolute value function is defined as, if we did a picture of the absolute value, it would give us a V shape. Remember that? Which basically means at 0 to the left, it looks like a line going down. But to the right of 0, it looks like a line going up. So there's some changes there. So what I want us to do in our calculator, we're very good at our calculator now, right? We're going to graph this function. Okay, so take out your calculator, and we're going to go to y equals. If you have stuff in there, get rid of it. I want to type in the absolute value of x divided by x. So to do that, we're going to hit math on the left side. Go to the right for number, and see where it says abs. That's absolute value. So choose number 1. The absolute value of x, hit to the right to get out of it, divided by x. So in y1, we're going to do the absolute value of x divided by x. Everybody have that? Then we're going to go to the window, and we're going to go -5 to 5, counting by ones, -5 to 5, counting by ones. And that's why we do chapter 1. We're comfortable with our calculator. We know how to graph stuff now. We know how to change our window. And we get this function. So, how to do the absolute value? Okay, does everyone have this picture? -5, 5, 1, -5, 5. Now, hey, this is not what we're used to now. If I talk about 0, coming from the left, y approaches -1. Coming from the right, what does y approach? 1. Something's going on at 0. Are we okay? That's what we're going to start talking about. And if I plug in 0, is it this or this? Well, then it depends on what happens. And let's talk about that. What happens at 0? Plug 0 in. If I plug 0 into the equation, just in your head, plug 0 into the equation, what happens? Can you divide by 0? What happens? It's undefined. You can't plug in 0. So if I come from the left, I get -1. If I come from the right, I get 1. So I'm thinking, is it -1 or is it 1? What's the answer? And what is the answer? What happens at 0? Undefined. These are the kind of things we can explore by looking at the left and looking at the right. Because we assume it's -1. Nope. We assume it's 1. Nope. It's actually undefined. And you're thinking, I can just plug it in to find out. But this is what we're exploring. We're exploring what happens as we come from the left and what happens as we come from the right. So that's what we're going to talk about. The limit from the left and the limit from the right. So how are you supposed to know which one's which? You see how this says x as it approaches c, but it has a little negative? That little negative means come from the left. I'm looking at it from the left. And if it says x as it approaches c plus, that means coming from the right. So I'm going to see what happens when I look at a certain number from the left and when I look at a number from the right. That's the notation. And we'll have some examples. If no direction is specified, then we're looking at it from both. So if I don't have the plus or the minus, it's because we're looking at it from both sides. And so from a two-sided limit that exists, the limit for the left and limit for right must be equal. So if you want it to work, what's coming from the left and what's coming from the right has to equal the same number. If they don't equal the same number, something's going on. You got something fishy going on. Okay, and that's what's happening here. If you look at this graph, if I come from the left, it approaches -1. If I come from the right, it approaches 1. Hey, something's going on at 0. And then when you plug in 0, you realize it's undefined at 0. They should be approaching the same number for the limit to be true. And that's kind of the theory stuff we're talking about. All this will get connected later. Again, notation. If I'm approaching 0 from the left, it approaches -1. If I approach 0 from the right, it approaches +1. They're not the same number. Something's going on at 0. So since the left and right hands are not the same, we say that the limit does not exist. Something's going on, and we know it's undefined. Okay, so let's look at this function. You don't need to know what the function is. You have the graph. And I want to look at the function at -1. So let's look at -1. If I start at -1, go to the graph, what is y equal? So the function at -1 is 1. Okay? Let's look at it from the left. From the left, what number is it approaching? 1. From the right, what number is it approaching? 1. So it exists. It works. Both sides are approaching the same number. Everything works out nicely. There's no issues at that point. It works. And you're like, I know it works. It's there. But it doesn't always work. For example, and again, to finish that one off, we say the limit as we approach -1 is 1. Why? From the left and right approaches the same number. It all works out nicely. But let's look at 1. Something weird is happening at 1. What's weird? Well, here's 1. As I approach from the left, what numbers are getting closer to? As I approach from the right, what numbers are approaching to? So it looks like everything's great. But what happens when you try to plug in 3? It's not filled in. So this one is leading me to believe the answer is 3, the answer is 3. But when we plug in 3, we realize there's a problem. So as we approach 1 from the left and right, remember if there's no number, it's saying from both sides, it approaches 3. But what happens when you try to plug into 1? It's not defined. Okay? So sometimes you can approach a number, but it still not be defined. And again, you're probably like, I can see that. This is when we can't see the graph, or we're making conjectures about the graph. This is some information about the graph. So let's talk about 2. 2, coming from the left, what number is it approaching? 2. Coming from the right, what is it approaching? 5. We've got a problem there. Okay? Are they approaching the same number? No, something's going on. And then I can't tell if it's filled. Yeah, it is filled in. It's filled in, so the answer would be 2. But are they approaching the same sides? No. So in this case, the limit as we approach 2 from the left is 2. As we approach from the right, it's 5. Therefore, the limit does not exist. They're not approaching. The limit does not exist. For the limit to exist, they need to approach the same number. They don't, the limit doesn't exist. And we can verify if you plug in 2, we get 2. So yes, there's an answer, but does the limit exist? No. For the limit to exist, left and right have to be the same number. Okay, and again, you're like, I don't see where this is connected. It will connect later, unfortunately, but this is getting us thinking what that means. So the function exists at x equals 2, but the limit doesn't exist at 2. So if you have 2 functions, f and g, and the limit as x approaches c for the function is L, and the limit as x approaches c of g of x is m, L and M are real numbers, both limits exist, then these are some certain rules that we can follow. Okay? I wouldn't worry too much about these. We're going to practice all these. But just some things we look at. If the limit as x approaches c is k, k for any constant. The limit as x approaches c of x equals c. We'll go over these, so don't worry too much about them. But these three are, they look like common sense and they should make sense. But if I want to find the limit as x approaches c of the first function plus the second function, that's the same as taking the limit of the first function plus the limit of the second function. If I want to take the limit as x approaches c of the first function minus the second function, it's the same as the limit as the first minus the limit of the second. Or if I have a number, a constant in front, I can pull that constant out. If there's a number in front, I can pull that constant out. We're going to practice these, so don't worry too much about them. But the big takeaway is, if I'm taking the limit of two things being added, I take the limit of each one added. If they're subtracted, take the limit of each one subtracted. If there's a number in front of the function, you can pull that number out. But again, we'll practice. Sometimes the symbols confuses us, but hopefully they're making some sense. And let f and g be two functions and assume that the x is limit as x approaches c, f of x equals L, and the limit as x approaches c, g of x equals M. Then here, if they're being multiplied, I take the limit of the first times the limit of the second. Okay? So added, take the limit of each one added. Subtracted, take the limit of each one subtracted. Multiply, take the limit of each one limit. Same thing with division. And if you have a square root, same idea. Okay? So, this is, again, going to seem a little weird, but kind of bear with me a little bit. Because you're going to be able to do it like that. If I want to take the limit as x approaches 2, that basically means plug in 2. But see how I have x squared minus 3x? We okay? Plug in 2 into the first one. So take the limit as x approaches 2 of the first one. You get 4. Minus, plug 2 into the second one. You get 6. Therefore, 4 minus 6 is negative 2. You're like, don't you just plug in 2? Yes. But it's just showing you that you take the one of each of them and subtract it. If you're being divided, limit as x approaches 4. We plug 4 into the numerator. We get 8. 4 into the denominator. We get 13. 8 over 13. It's just showing you that you can take the limit of top and bottom, same thing, and you get the same answer. But to you right now, it looks like we're just plugging them in, and that's kind of what we do. The limit as x approaches c f of x for f of c for any polynomial function, and the limit as r of x equals rc for r for any rational function with a non-zero denominator of x equals c. Bottom line, if it's polynomial, then the limit will exist. If it's rational, you got to be careful of the denominator. Again, once we do examples, it will make more sense. Okay? So here's what I want you to do. Here's what I want you to do. I want you to write this down. And notice how it's being subtracted and added. That means you just take the limit of the first one minus the limit of the second one plus the limit of the third one. Are we okay? Which basically means just plug in the 2 for the x's. Are we okay? But understand that you can take the limit of each one. So see what you end up for an answer. I'm going to write the work. But I know in your eyes you're like, I'm just plugging it in. You kind of are. But it's just showing how limits work. So if we have the limit as x approaches 2 of 2x to the 4 minus 3x squared plus 1, that is the same as the limit as x approaches 2 of 2x to the 4 minus the limit as x approaches 2 of 3x squared plus the limit as x approaches 2 of 1. If you plug in 2, You get 2 to the 4th, 2 times 2 times 2 times 2 is 16. 16 times 2 is 32. Minus, plug 2 in, 2 squared is 4. 4 times 2 is 12, plus 1. There's no number to plug in. That gives us 32 minus 12 is 20. 20 plus 1 is 21. Okay? Again, all we did was plug 2 in. But that's what the properties show us. The next one I'm going to kind of show you. You can jot it down, but it's the same idea. So for the next one, if I had the limit as h approaches 1 of the cube root of 2x to the 4 minus 3x squared plus 1, using the properties, basically all that means is we can take the limit of x approaches 1 inside the cube root. So if we plug 1 in, 1 to the 4th is 1, 1 times 2 is 2. 1 cubed is 1 squared is 1, 1 times 3 is 3. 1, 2 minus 3 is negative 1. Negative 1 plus 1 is 0. The cube root of 0 is 0. So it looks like we're just plugging it in. But we're looking at the idea of taking a limit. We're looking at the idea of taking a limit.
What is it?
Sorry?
What is the exact meaning to take
The take the limit is as you approach from the left to the right, what numbers are approaching. So at this point, it's kind of like, why are we doing it? Why are we just plugging it in? We're going to be looking at, and again, this is kind of future talk, right? So if I have a revenue function that goes up and goes down, I want to find the maximum. So if I can figure out where it is from the left, figure out where it is from the right, it will lead me to the maximum. Does that make sense? Right now, we're just kind of looking at it as functions and symbols. It's going to show up later. And it's all going to lead to something called derivative. And how to find a derivative is using limits and how things change at a very specific point. So this is all background in this thing. Okay? So in this case, the limit as x approaches 2, 2x plus 3 over 3x plus 2. Basically, we're going to plug in 2. We're going to take the limit as x approaches 2 of the numerator, 2x plus 3. So 2 times 2 is 4. 4 plus 3 is 7. We're going to take the limit as x approaches 2 of the denominator. So if I plug in 2, 3 times 2 is 6. 6 plus 2 is 8. Our answer will be 7 over 8. Just a second to write that down. In the next one, if I have the absolute value of x over x, x is the limit as x approaches 4. If we plug 4 into the limit as absolute value of x, that gives us 4. The limit as x approaches 4 of x, plug in 4. We get 4 over 4, which is 1. Now again, all these are working out nicely. Soon we're going to get to ones that don't work out. What if it doesn't work out? What if we get undefined? What happens there? Okay? So here's where things get a little different. So in this function, it's saying when your value is less than 2, use this one. When your value is greater than 2, we use x minus 1. Okay? So here, understanding our symbols and all that, the limit as x approaches 2, what does the negative 1 mean? From the left. So am I going to use the top function or the bottom function? The top one, when it's less than 2. So take 2, plug into the top one. What do you get? 2 squared is 4. 4 plus 1 is 5. So the limit as x approaches 2 from the left will give you 5. Now find the limit as x approaches 2 from the right. So now that it's coming from the right, do I use the top one or the bottom one? The bottom one. 2 minus 1 is 1. So here's where things don't work out. So from the left, it approaches 5. From the right, it approaches 1. Stop there. See how I got that? Again, it's not a nice one where it works out. This one has some issues. Does the limit exist at 2? Yes or no? No. Why? The numbers are different. That's it. That's all you got to get. All this background, all this stuff is setting you up for that. Okay? And you're saying, like, oh, it's not that hard. It's pretty easy. That's calculus, right? I'm not saying calculus is hard. It's where it all comes from. Now, C says plug in 2. Huh. Which one has the equal to? Which one has the equal to? Neither one. So can I plug in 2? Nope. 2 is undefined. So since the one-sided limits are not equal, neither one of them have an equal, it does not exist. The limit doesn't exist. From the left, from the right, they don't match. Now, if they did match, if this one approaches 5 and this one approaches 5, I could say that it's going to 5. But they don't match, so I can't say that. They don't match, so I can't say that. Okay? This is the bottom line. I know it doesn't sound earth-shaking, but it's the beginning of calculus. And when you try to plug into, you can't, it doesn't exist. Okay? So, from the left, it approaches 5. From the right, it approaches 1. Since they're not the same numbers, the limit does not exist. The last thing we talked about is, can you plug in 2? I can't plug in 2 because there's no equal to, and it doesn't, and there's no point at 2. If the limit as x approaches c f of x equals 0, and the limit as x approaches c g of x equals 0, then the limit as x approaches c f of x over g of x is indeterminate. Bottom line, if you plug in and the top is 0, if you plug in and the bottom is 0, we call that indeterminate. So if you get 0 over 0, it's indeterminate. Indeterminate means I don't know what happened. I have to explore further. If you get 0 over 0, that doesn't mean it doesn't exist. It may or may not exist. So if you get 0 over 0, don't stop there. That's an indeterminate, not sure what the answer is. It may or may not. If you get 0 over 0, you can't stop there. It may or may not exist. You got a little bit more work to do. So if you get 0 over 0, it just means you have a little bit more work to do. And just because you get 0 over 0 doesn't represent a real number, and it's never used for the valuable limit. So let's look at this example. If I am taking the limit as x approaches 2, basically that says plug 2 in for x. Are we okay? 2 squared is 4. 4 minus 4 is what? 2 minus 2 is 0. You get 0 over 0. You would assume, doesn't work, move on. No. If you get 0 over 0, that means you're not done. There's a little bit extra work to do. And guess what the work is? It's algebra. That's why we spend so much time on algebra. So what they want you to do when you get 0 over 0, explore further. X squared minus 4 factors to x plus 2, x minus 2. I'm not teaching that. That's what we covered before, right? What happens to the x minus 2 over the x minus 2? And we're left with x plus 1. Plug 2 in. What's 2 plus 2? 4. So all we're saying is, when you get 0 over 0, you can't stop. It may or may not exist. You got to take it a little bit further. That's all we're saying. Okay? So if you get 0 over 0, you're not done. That's called indeterminate. You got to take it further. Most likely there's some algebra work to clean it up. Yep.
Is that not just like checking the word?
What happens is, if I didn't go over this, and you got 0 in the denominator, or you got 0, you'd be like, oh, undefined, stop. This is saying, wait a minute, you can't stop. There's a little bit more work to do. Think of it that way. Because normally it's 0 when either the answer is 0 or the answer is undefined. But 0 over 0 is telling you, I don't know yet. That's all. Good question. So If the limit as x approaches c, f of x is L, and the limit of x approaches c is 0, then it does not exist. If you keep working on it and it ends up being 0, then it doesn't exist. Okay? So here, this is the one I want you to work on. Determine if it's a 0 over 0 and if it exists or not. So plug in 2, see what happens. Okay, if you plug in 2, what does the numerator become? If you plug in 2 the denominator, what does it become? 2 squared is 4, 4 plus 4 is 8. Is that a 0 over 0? No. That means we can come up with an answer. Be careful, what's 0 over 8? Is that 0 or undefined? Remember, there's a difference between these two. Okay? The top one is 0. The bottom one is undefined. So be careful about that. I'm not sure if this is a class I told you. They taught me a long time ago. 0's on top, it's okay. If 0's on the bottom, no way. If that helps you remember. The real answer is, if you divide it, 8 times 1 gives you 0, 0 does. 0 times 1 gives you 8, you can't. That's the real reason. Okay? But again, review. What's 0 over 8? 0. So it's not 0 over 0. We actually get an answer. Therefore, the limit as x approaches 2, x minus 2 over x squared plus 4, the answer is 0. And if I graphed it from the left, from the right, it would both approach 0. Try the next one. And if it is 0 over 0, that means you have more work to do. If it is 0 over 0, then you have more work to do. Oh, I meant to do this. Okay, if I plug 2 into the original, I get 0. Plug 2 into the denominator, I get 0. Does that mean I can stop there and call it undefined? No. 0 over 0 means indeterminate. You got to take it a little further. And when you take it a little further, this factors in x minus 2, x plus 2. X minus 2 over x plus, x minus 2 over x minus 2 becomes 1. So really, we're looking at 1 over x plus 2. And when you plug 2 in, what do you actually get? 1/4. So getting 0 over 0 doesn't mean you're done. It means that there's more work to be done. You have to explore a little further. It may or may not exist after that. I don't know. But it means you have some more work to do. You have some more exploring to do. So the answer is, you get 0 over 0, which is indeterminate. And then you factor algebra, you get 1/4. Okay? Try this next one. Now, again, we're factoring the same stuff. You could get a lot of other things to factor. So factoring is going to be the hurdle for some of you. That's why we spend so much time in Appendix A and Chapter 1. And I'm hoping factoring was not the problem. Okay, so for this one, if you plug in 2, we get 0, we get 4 over 0. So it is not a 0, 0. And what's 4 over 0? Undefined. So this one, you don't have to factor further. We didn't get 0, 0. We got 4 over 0, which makes it undefined. We okay? And the last thing is, pretty soon, the beginning of calculus, which starts with slope. Slope goes to rate of change, which is rate of change. It's going to lead to this. This is going to be our definition of a derivative soon. The limit as h approaches 0, f of a plus h minus f of a over h. We touched upon this before because it's going to show up again. But tied to what we're doing, if you work this out and the top equals 0, which it often will, then it's an indeterminate form. You got to keep going with it. Okay? So the top will often equal 0, 0. That will often happen. But I'm going to give you a preview of why we spend so much time on algebra. This is a preview of where this is all going. Okay? We touched upon this a little bit before, but I'm going to remind you. So here is where your algebra should be at for us to be able to move forward. So this is the definition of a derivative, which we'll go over later. And let's see if we remember what this means. This says the limit as h approaches 0, go to the function, and what am I going to plug in? Not yet. I'm going to plug in a plus h. So where there's an x, what am I going to put? A plus h. So let's be clear. We did this before. If this was f of 4, I plug in 4. F of 5, I plug in 5. F of a truck, I plug in a truck. But what am I plugging in? A plus h. We okay? Minus f of a. So basically, everywhere there's an x, I'm going to plug in a all over h. Now, tied to the lesson, if I plug in 0 for h, that becomes 0. The zeros in the denominator, we're going to have some issues. But let's do the algebra.
Don't you want to simplify first?
But that's what we're going to do. We're going to simplify first. But to this lesson, 0 is going to be an issue to the numerator. I'm going to take it all the way and give you a little bit of the future. So if we clean this up, the limit as h approaches 0, 2a plus 2h minus 3 minus 2a plus 3 all over h. Algebra, algebra, algebra. What happens to the numerator? Two a minus 2a. What else happens? So what I'm left with is 2h over h. So if I plugged in 0, you would get 0 over 0. That's indeterminate. But we know what happens to h over h. Then we're supposed to plug in 0 for h. There is no h, so we're left with 2. In the future, the very near future, we're going to say the original function is 2x minus 3. The derivative function, f prime of x, is 2. And this is going to be why it's the derivative. That's the future. Okay, we're going to do derivatives.